All right, everyone. Um, Back again to start to get serious about talking about projectile motion. So, first of all, just maybe a quick definition. What is projectile motion? What do I mean when I say projectile motion? So here's what my definition of projectile motion is, and I think it's pretty accurate. So projectile motion is the motion that an object sort of, I don't know, experiences, the motion of an object as it flies through the air, where the only force acting on that object is gravity. Okay? So, projectile motion isn't necessarily just things that are flying around. Um, Something like an airplane. I mean, gravity is acting on the airplane, but there are also other forces, other significant aerodynamic forces. Um, there's propulsion, there's an engine that's pushing it forward and stuff like that. So something like an airplane is not a projectile. At least we don't want it to be. We want it to stay up in the air, right? Um, so yeah, so that's basically it. Um, what I love about projectile motion is like you can have a lot of fun with it. So I'm going to be doing some demonstrations where I throw a football and it flies through the air like a projectile. I just did something. I just recorded a very brief video using these two spheres. So that's pretty cool. And then, of course, I have an air-powered rocket that we're going to be doing some stuff with later also. Um, so yeah, that's the basic intro to projectile motion. Um, some facts about projectile motion. Before I get into the practice problems, I will just say some things about it that are kind of important concepts. Um, Again, first thing, the main force, the only force involved here is the force of gravity, acceleration due to gravity on Earth is 9.8 meters per second per second. Okay, so what that means is if I drop something straight down, it starts with zero velocity, and then if I let it go and it falls for 1 second, after 1 second, its velocity is now 9.8 meters per second. Okay. If I let it fall for 2 seconds, then it's whatever 9.8 times 2 is, and so forth, right? So you can use that fact in lots of ways to answer some really interesting questions. So questions like, if I'm standing on top of a building and I drop something and I can time how long it takes for it to hit the ground, well, I can do a very simple calculation to determine how tall that building is. Pretty cool, right? If I am, if I'm throwing a football and I'm sort of really carefully measuring the angle at which I'm throwing that football, and I throw it with the same velocities every single time, I should be able to predict exactly where the football will land. I should be able to predict how high above the ground it will go. I can do just about anything in terms of calculating the path of the trajectory of the ball that I throw. Okay, which is important if you're doing things like trying to knock down bowling pins with a football, which I will probably be doing tomorrow, as long as it's not raining. Okay, so I think that's about it. I think any other like basic or important concept about projectile motion that I need to talk about and that you need to hear about will probably come out as I talk about the answers to these projectile motion practice problems. Okay, sometimes the best way to learn the concepts is to just do some examples. So let's do some examples. So we'll do the 2 questions on page 1, and then I got to hop on a virtual office hours call. So hopefully I can knock these out in 5 minutes. We'll see. Question number 1: a rock is thrown horizontally from a cliff at 25 meters per second. Okay, so here we go. There I am, standing on a cliff, holding a rock for some reason, and I'm going to throw it horizontally with an initial velocity of 25 meters per second, and all of that velocity is pointed horizontally, okay? What will its horizontal and vertical velocities be after 2.0 seconds? Okay, so two separate questions here. Horizontal velocity, and actually, I'm not going to write it like that. Here's how I'm going to write it. I'm going to say v with a little h stands for the horizontal velocity, and v with a little v stands for the vertical component of the velocity, because in a way, there's two different types of motion happening here. With projectile motion, you have horizontal motion and you have vertical motion happening at the same time, okay? So horizontal velocity, okay, so first important concept to realize here is that in all of these problems we will assume, and it's a pretty correct assumption, that the horizontal velocity throughout the entire path as it flies through the air, the horizontal velocity is always constant. Whatever it starts with, that horizontal component of the velocity stays the same the whole time, okay? So that means at 2 seconds, the horizontal velocity, so this is part A, at 2 seconds, the horizontal velocity is still 25 meters per second, okay? Now the vertical velocity, that's the one that changes. That's the one that gravity actually influences. And so at 0 seconds, it has 0 vertical velocity. At 1 second, the acceleration due to gravity has sped it up in the vertical direction, and now it's going 9.8 meters per second. And actually, we'll say negative because it's moving downwards, okay? So after 1 second, it's negative 9.8. After 2 seconds, it would be, what is that, 19.6? Negative 19.6, did I do that right? Yep, 19.6 meters per second. So part A, there you go. There's the two components of the velocity, okay? Part B, what will its velocity be after 3 seconds? Okay, okay, and now it's not saying the difference between, it's just saying overall velocity. What is its overall velocity at 3 seconds? And remember, velocity includes direction. So we don't just need to say, we're not just asking how fast is it going, but also what direction is it going in. So, oh, so here's what's happening. It's going like, right? And then it hits the ground or the water or whatever's down there, okay? So at 3 seconds, we'll say it's right around here, okay? We know that its horizontal component is 25 meters per second. At 3 seconds, its vertical component is whatever 9.8 times 3 is 29.4 meters per second. But it's what we see, right? We don't see, like our eyes don't separate really the vertical and the horizontal. What we see is the overall. At that exact moment, right? The path of this rock is kind of going in this direction, right? It's going to, and as it goes along the path, the angle that arrow makes, kind of it changes as it falls, right? So we got to figure out two things. We got to figure out first, what is the magnitude of that? Well, hopefully you're all thinking to yourself, that's a right triangle. If I'm trying to find the length of a hypotenuse, I just use the Pythagorean theorem. Pythagorean theorem would say that the overall velocity squared is equal to 25 squared plus 29.4 squared. That's going to come out to, let's see, 25 squared plus 29.4 squared, and then take the square root. Boom. 38.6. So overall, right, the overall velocity is 38.6 meters per second, which makes sense because the hypotenuse has always got to be greater than the two legs, and this is, right? So that seems reasonable. Now the other thing is, what is this angle? We have to figure out what's the direction. It's not going down. It's not, it's purely going down, and it's also not purely going horizontal. It's going at some angle to the horizontal. So to determine that, you can use some trigonometry, right? So if I know the opposite and the adjacent, then the tangent ratio is what I'm going to use. The tangent of that angle, which we'll call theta, is equal to opposite over adjacent, which is 29.4 over 25. To solve for the unknown angle, I am going to do the inverse tangent of both sides of that equation. So really what I'm doing is I'm doing inverse tangent of 29.4 divided by 25. Boom. It tells me 49.6 degrees. Yeah, I mean, I'll just call it 50 degrees. So this angle is 50 degrees, so I would say theta equals 50 degrees. Here. So, that's the full story. What will its displacement be after 3 seconds? Okay, this is part C. What will its displacement be after 3 seconds? So remember, displacement is total distance traveled from where it starts. Where it starts is here, and at 3 seconds, it's like here, right? So how far has it gone? Well, this, I think, is going to be another Pythagorean theorem question. If I know how far it falls, and I know how much it's gone horizontally, then I can solve for the hypotenuse there, all right? So, let me clean this picture up a little bit. Okay, let me kind of start over. Because, let's see, sometimes it's good to redraw the picture to kind of get your mind in the right spot. So it goes, we'll say that's it at 3 seconds. How far does it go horizontally? Well, that's not too difficult because it's 25 meters per second constantly times 3 seconds. In the horizontal direction, it has traveled 75 meters. Okay. Now, how far has it gone vertically? That's a little bit trickier because it's accelerating. If we just kind of do the graph thing, the time that it's falling is 3 seconds. This is a velocity time graph. The time that it's falling is 3 seconds. We know that after 3 seconds, the velocity was, 9.8 times 3, 29.4, right? 9.8 times 3. Yeah, 29.4. So this right here is 29.4. The distance traveled is the area of that triangle. So distance equals 0.5 times 3 times 29.4, boom, 44.1 meters. So this is 44.1. The hypotenuse, I think I'm going to stop here because I think you can handle the doing the Pythagorean theorem here, plus I'm 3 minutes late for my call. 75 squared plus 44.1 squared equals the displacement squared. So take the square root of that and you've got the total displacement. All right, that is it for question 1. I will be back in a minute to talk about the other questions on this practice problem sheet. Cheers.